So part 2 of the Chapter 19 Organometallics mini lectures will focus on the application of some new organometallics that have really incredible applications to organic synthesis. So, last mini lecture we just introduced the basic mechanisms that are kind of new elementary steps. Similar but different enough, but these new elementary steps that happen to come into play whenever we have transition metal organometallic complexes. And just to make it quite clear, when we talk about organometallics, what we're talking about is anything with a carbon-metal bond. So that's what an organometallic is, and these complexes do oxidative addition, reductive elimination, and beta hydride elimination. So let's see what they can do. The first one we'll look at is SuzHeck coupling. Now, I know what you're thinking. We already learned about cuprates. Why do we have to learn about something else? And I'm just pointing out that these named reactions are actually named after real human beings. This is a picture of good old Akira Suzuki, who won a Nobel Prize for this chemistry. So that's why we need to learn it. It's pretty important chemistry. The overview is that an aryl halide, so a halide on an aromatic ring, plus a borane, whatever that is, well, we'll see in a second. Those two get pieced together kind of like a jigsaw puzzle. Or from my era, Tinker Toys. How does it happen? It happens because magic ingredient of palladium 0 is part of the mix. So here's an example of a SuzHeck coupling. So here is my aryl halide. Key here is that you have a bromine, typically bromine, sometimes iodine, on your aromatic ring. That's essential. That, right there, is where the coupling is going to take place. The other partner is the aforementioned borane. Alright, well, you've seen boranes before. Yes, you have. Remember this reaction? What does that give you? That gives you a borane. There it is. A boron-carbon bond. Here it is, a boron-carbon bond. So the important thing that you want to focus on right here is that this organic bit that is connected to the boron is going to be the other partner, the other piece that connects to that carbon. So what about all this stuff? Well, that's just junk. You can call those ligands. They're things that need to be there to make the boron complex stable. We're not going to go into any of this in great gory depth, but just know that these aren't hard to make at all. So, bottom line, if you take your aryl halide and your borane and throw in the magic ingredient, what's going to happen is my palladium, which has 4 triphenylphosphine ligands around it, that's palladium 0. So what that's telling you is that my palladium 0 is going to do an oxidative addition right there. The next thing you know, my borane is going to add that bit to my palladium. So I'm going to have PD with my, let's see, I've got methoxy here and methoxy here. I'm going to have that on my palladium, and I'm going to have this on my palladium. What does that tell you? Ha! It tells you reductive elimination. Now that they're both on the palladium, I can get that reductive elimination to take place. This guy comes over there, kicks off my palladium, and voila. Tinker Toy chemistry. I've just made that new, bold carbon-carbon bond. These reactions work under very mild conditions. They work in very high yields. So, SuzHeck coupling is another way of coupling together 2 organic pieces to make a new carbon-carbon single bond. A similar reaction is the Heck reaction. This is Richard Heck, no longer with us. He invented the Heck reaction, which basically takes, in a similar manner, an aryl halide, but instead of a borane, it couples it with an alkene. Again, catalytic palladium 0 is the magic ingredient. So here's our Heck reaction. What you want to zoom in on is, is it going to be the bromide, or is it going to be the iodide where the coupling is going to take place? Palladium 0, and this is actually a typo. That's supposed to be PPH3 for palladium. That's my palladium 0, and it's going to oxidatively add right there. Turns out iodide is more reactive than bromide. And then what? Well, this one really looks like magic. Wow, that's crazy. How did that happen? It's as if somehow or other that hydrogen just kind of got ripped off and then it got plugged in over here. What the heck is going on? Well, it's not magic chemistry, and it's not as simple as ripping off a vinyl hydrogen. That just doesn't happen. But before we go to describe the mechanism in a little bit more detail, I just want to point out, this is in the presence of a carboxylic acid. You know you could never do that with a Grignard or organolithium. So this is pretty impressive chemistry. So, very high functional group tolerance, and again, you have retention of configuration where it applies. So, I will say, the book does not emphasize regiochemistry to any great extent, and the regiochemistry is not trivial. When we look at the mechanism, you will see what I'm talking about. So basically, we know that we're going to get this palladium species. Now what? Well, this is a little bit more detailed than the textbook, but basically what happens is your alkene is going to coordinate to the palladium. We can rewrite this as if it is, let me get rid of that oxygen, extra oxygen there. We can rewrite this as if it is what we would call a metallocyclopropane. So these two represent the same thing. Well, you know, that's a lot like an epoxide. And I know that epoxides are really easy to break open. And so if I use my organometallic to slide over and break open that epoxide, I can give that pair of electrons back to my palladium. So that gives me this right here. And what does that lead me to? Ha ha! That leads me to the possibility for a beta hydrogen elimination. So that's how this miracle chemistry takes place. So I end up with my product, and again, don't pay any attention to the particular stereochemistry I'm showing here. It looks like it might give, this kind of looks like it might give Z. We're not going to go into the great gory detail of stereochemistry. It's really interesting. If you want to know more, take an advanced organic class that talks about organometallics. But basically, the whole thing is oxidative addition. This moves over, kind of like opening an epoxide, and then we have a beta hydride elimination. Voila, your product. Finally, I think the most magical of them all is metathesis. This is Grubbs, I think it's Robert Grubbs, I think that's right, who is still with us, and he came up with unbelievably important reaction that is used a great deal to make polymers. We're going to show how it's really important in organic synthesis as well. The key player here is not palladium, but ruthenium. This is an example of Grubbs catalyst. There's a whole bunch of them. The ligands can be this crazy tricyclohexylphosphine right here, or another popular ligand is this guy, which is a carbene. We learned about carbenes when we learned about how to make cyclopropanes. These are not the important details. The important details are what happens when we carry out the Grubbs metathesis. And the easiest examples to understand are the ones where we close a ring. It's called ring closing metathesis, RCM. And it's kind of miraculous. What is going on here? I add this catalytic amount of my Grubbs catalyst, and what appears to happen is I kind of chop those two alkenes in half. Obviously, I am losing these two CH2s, and I am putting together those two carbons to make this product. So, I can go into some detail on the mechanism. The book gives you some detail. It's probably helpful, but it's not certainly something you're going to need to know for an exam. So, look over the mechanism. Let me know if you have any questions. Alright, so those three new reactions, the Suzuki, the Heck, and the Grubbs, are very, very powerful. They're all mild. They're all high yielding. They work with great control. So they pretty much work magic, but it's not really magic. You can use the simplified mechanisms I've presented in this mini lecture or in CARDI to give you a sense of what the product will be. To summarize in a nutshell, copper is going to, in this example, couple with anything. I'll just put here on the side. Remember, cuprates do 1,4 conjugate addition. That's the other place where we've learned about cuprates. Palladium plus boron means that's the Suzuki reaction, and that couples aryl halides to other things. And palladium all by itself, actually with an alkene, is the Heck reaction. So you couple aromatic with an alkene. That actually ends up giving you an alkene substituted aromatic. And in the Suzukis, they're typically, could be this, could be this. Bottom line is, in the Suzuki, you're focused right here, and the Heck is the one that kind of is like you pulled this guy off and stuck it onto the where the halide was. All right, recognition, doing practice problems will help a ton. Finally, the metathesis reactions stick together two alkenes with the loss of some carbons, but it's such a powerful reaction we don't even miss those carbons. Gives you a new alkene. So, good stuff, crazy stuff, probably time for a good joke. Too bad I don't have a good joke. I have a really bad joke. Because my sister was talking about how the right signal light on her car wasn't working. And so she asked me to check it. Yes, I stood at the end of the car, looked at the rear of the car, and she turned on the signal, turned on the blinker. And I looked and I said, yeah, it's working. Oh, wait a minute. It's not working. It's working! Wait a minute. It's working! Get it? You know, it's blinking on and off. Yeah, that was a really bad joke. Okay, I'm sorry. We'll see you in class.